Thank you everybody who logged on today. Today we're going to talk about geospatial analysis in Python, and I'm using the example of exploring Chicago to do that. And so basically, the purpose of this project is that it was kind of a initial installment in a series of projects aimed at building a data-driven tool that provides guidance of where I would want to live in Chicago. And I'm using that goal as the ultimate driver for today's focus, which is geospatial analysis using Python. So the agenda today will be, I'll give some high-level insights from my analysis, and then I will walk you through the journey of how I got there, giving you an overview of what geospatial analysis is, an introduction to GeoPandas, how to combine different data, and also visualizing spatial data. And lastly, I'll give a high level of the approach to analysis that I took in this project. So when you think about, or when I think about where I would want to live in Chicago, there's three main things that I thought would be important. A, is it safe? B, can I get around easily without a car? So how is public transportation? Because I don't like driving that much. And also, like, what are my options for going out around me? Are there a lot of food options? Are there bars, cafes, etc.? Well, this analysis is gonna dig into these three things. The map on the right is an example of the kind of simple maps you can build using geospatial analysis, pulling the different data sources together and kind of visualizing that data as far as density of some of your parameters, etc. So we'll learn how to generate a map like this as we walk through the presentation. Okay, so high level insights. So some of the things that I found through my analysis was that certain crimes are more likely to happen in certain parts of the city. So for example, theft happens downtown and in areas with more bars and restaurants, which that makes sense. Whereas violent crimes happen more so on the south and west sides of the city, with some neighborhoods being significantly more dangerous than others. And then the data indicated that some parts of the city may be more heavily policed than others, and I'm going off of arrest rates as an indicator of this. Whereas neighborhoods like Uptown, which is on the north side, is on the bottom 50% for violent crimes, but actually has the third highest arrest rate. Whereas, the near South Side has a high amount of violent crimes and also a high arrest rate. So, yeah, just an interesting contrast there. The other insights, again, around transportation and kind of stuff to do is that in general, the South Side seems to be more poorly served by the CTA, Chicago Transit Authorities, L, that's our train system, than other parts of the city. Even though the L has, an extensive network outside of city limits on the north side of Chicago, which tends to be more affluent. And also the north side has by far more options for restaurants, bars, and cafes. All right, so let's dig into the technical stuff a little bit. So what is geospatial data? It's any data that includes information or describes something based on its location. And there are two different types of representations of spatial data. One being vector data. So a location is described by a point, like a lat long, or a line, or even a polygon, so different shapes. The other type of representation is raster data. And in this representation, the world is shown by a pixelated grid where each cell represents a geographic location. We're going to be looking at vector data. We won't be looking at raster data at all in this analysis. And also good to know is the file types for spatial data. So there are shape files. They usually come in a zip, and you need all three of them for things to function properly. When you start using them in Python, you need all three to be in the zip. But .shp is the extension for that file. And then another common one is GeoJSON, which we won't be using in this presentation either. Okay, so the Earth is an imperfect sphere. CRS, what is CRS? It's the Coordinate Reference System. And the reason that I'm mentioning this here is because, you know, when you get into talking about geolocations and space on the Earth, we know that the Earth is round. However, you know, different parts of the world is shaped differently. Some parts are very mountainous, some are valleys. And so, of course, it's not a perfect sphere. So that's going to affect things like distance measures when you have different parts of the Earth that is kind of like the shape is not smooth, I guess it's the best way to think of it. So there are two different types of CRS, geographic coordinates, which define a location using a worldwide coordinate system. Again, think longitude and latitude. And then there are projected coordinates, which actually flatten the 3D data of the Earth onto a 2D map representation. And again, this is helpful because certain parts of the world have different, granularity isn't the word, but it's just shaped differently. So you might have to use a specific CRS depending on where your analysis takes place. So what I'm using for Chicago may not be relevant or a good use if you were doing an analysis in Germany. So just something to keep in mind when we dig into the code, that CRS can affect your analysis. Geospatial in Python, GeoPandas. So I'm assuming everybody here has, you know, a little bit of understanding of Python. And of course, if you do, you've used pandas. GeoPandas allows you to work with spatial data in a manner that's very similar to pandas. So you're using a geo data frame and able to do some of the same functions like group bys and pivots and things of that nature that you would do on a regular data frame, pandas data frame. The main difference is that a geodata frame has an active geometry series, and it's always going to be named geometry. And this is basically your shape that we talked about, whether it be a point, a line, or a polygon. It's going to be the indicator of the location of a specific set of data on a row. You can relate different location data through spatial joins. So let's say, you know, I talked about wanting to know if a place is safe. If I had a bunch of data that was crime data, and each crime takes place at a certain point, a latitude, longitude, and I wanted to see how much crime was in a specific neighborhood. A neighborhood would be another shape. a polygon, let's say it's a circle, I could do a join of those two different data sets to see which of those points fall within or intersects with that polygon to actually be able to get an idea of how much crime is in that location. Another thing you can do with GeoPandas is create buffers. So it's basically drawing a radius around the geometry. So I talked about public transportation system, the train stations. If I wanted to know how much crime happened within a half a mile radius of a specific train station, I could draw a buffer and then do some of the same type of functions that I did when I was joining the other two data sets. Okay, so I am going to move to the Jupyter notebook. We're going to go through how to combine spatial and non-spatial data from different sources, how to create maps and visualize spatial data, how to identify spatial events with a radius or buffer, and then the overall analysis or approach. I'm gonna pause here before I go to Jupyter just in case there's any questions. Nope.
I have a quick question.
Okay.
The notebook that you, well, actually two, the notebook that you're going to show us,
Mhm.
would you make available to the attendees along
Yeah.
with files, along with
Yes.
files?
Yeah, we'll put that on our BlackTIDES GitHub.
Okay. And the second question, is there room in this presentation to delve into how you pick a CRS based on like the area or the location, or if it's beyond the scope, that's fine. But I just wanted
Yeah, it's beyond the scope, but definitely just Google it and you'll get some insights. There is a site that goes in depth of different CRSs for where you are and other, like when you Google it, more guidance to how to choose one depending on exactly what you're trying to do. So yes, out of scope here, but definitely a Google search, you'll be able to figure it out pretty easily.
Okay, thank you.
You're welcome.
We have a question in the chat. Can we convert any CRS for use in any analysis to fit the geospatial data of that region? From Lolu.
You can convert any CRS to any other CRS. However, you might get wonky results. Yeah, so you'll see in the notebook, like it's simple to just set a CRS. However, it could affect your results especially if you're joining things, if you have two different CRSs, they might not join properly. So you want to make sure that A, you've picked the one you want, and B, if you are joining two different spatial data sets, that they have the same CRS. All right, so you guys know Python, import your libraries of note is GeoPandas, which will be GPD. Like I said, we're not doing anything fancy. We're just going to use matplotlib like normal. So yeah, all good. The data. So there's several data sets that I use for this. One of the main ones being community area and block group boundaries. So I went to the city of Chicago's site for data, and they actually have shape files that provide the shapes for the polygons when we're talking about community boundaries and census block groups, which a census block group is the smallest level of like mapping for a census area. So that's what I went with. Other data sets in this analysis, business licenses, So I talked about wanting to know what restaurants, bars, etc. was around me. Of course, a business needs a license, so this I thought was a good data set to represent those things that are around. Crime data, and also data for the location of L stops, which again, L is the train system in Chicago. And all of these data sets came from the city of Chicago's public site for data. So yeah, we're gonna just import the data. There's extra data sets here. I used other things in this analysis, but I'm not gonna cover them in this presentation. We're just gonna focus on the 3 ones that I've been mentioning. Once we read in the data, we can quickly start in with our geospatial analysis. So I talked about the community area boundaries is a shapefile, that's .shp, which I mentioned before. And the good thing is, like I said, that these type of files will have a geometry, and matplotlib, or actually let's expand this, it automatically knows to map the geometry. So just by simply plotting this, it will plot the boundaries, and I added the text and colors and things. But right away, we get a map of Chicago neighborhoods just based on the community boundary data set that we pulled from Chicago Public Data. I also pulled the data set at the census block group level, which I mentioned, again, a shapefile. And I just wanted to show you guys here the difference between a community area map, obviously larger boundaries, versus a block group map. You can see that the boundaries are much more granular. And then here, I'm just going to note this because I mentioned that a GeoPandas data frame is very similar to a Pandas data frame. When I got this data set, it had a lot of different counties in Illinois. So I filtered only the county that was Chicago, Cook County, just like I would a normal data frame. And it also included water areas as polygons or shapes in the data set. If you know Chicago, you know here is where Lake Michigan is. And so that was distorting the map, having a huge block of Lake Michigan being there. So I looked for the largest water area, that's for max, and then I filtered it out of the data frame, thus leaving us only with the polygons or census block shapes that would be relevant for this analysis. So this is Cook County. This is how the data frames actually look, just so you can get a quick view. I told you there were counties, which I filtered to just Cook. I talked about geometries, every shapefile having a geometry. This is the block group level. The geometry is a polygon, so it's a shape. And then there's other bits of data in here that we don't really use in this particular analysis, but things like land area, water area, if that polygon had water in it. And this is the data set for the community block groups boundaries. Again, another polygon geometry, and the community name is here. Okay. So one of the key things that I talked about was being able to join different data sets together. Here, I'm just going to join my block group level data with my community level data, because as I start layering on different data sets, I want to be able to fluidly go between block group and community area group So to do that, you see here we have the two data sets. First off, I like to create a column naming the specific geometry so that once these get combined, I'll still have a reference point to be able to know which geometry is which in case I ever want to switch an active geometry. So for both data sets, I just create a column naming that geometry for that data set. Here, I am making sure that both of these data sets have the same CRS, which I talked about earlier in the question we had about CRS, wanting them to be the same before we make a join. And then to make that join, we would just use SJoin. It's very similar, like I said, to pandas. It's going to be a left join. OP, I'm using intersects. Usually it will get the job done. There are other options. Be sure to read the documentation to see what option makes the most sense for what you're trying to do, because if you use the wrong one, you might get some results after the join that you don't want. But yeah, once you do that, you will have joined your data sets. My joined data set is just shy. This is a mapping of the data set. Here we can see that the active geometry is census block group because we can tell these are the granular census block groups. Below, I'm going to demonstrate what I talked about, fluidly changing active geometries. So for the shy data set, I just created a quick little other data frame. And then I am going to set the community geography geometry to geometry, which is going to make it the active geometry. And then once I map it, now you can see that clearly the active geometry is community areas and not block groups. And you can tell by the larger boundaries there. Okay, so as I said, there are three things that we're paying attention to here, transportation, stuff to do, so businesses, and crime. And I have in this notebook the three, but I'm only going to look at one because we're time, and also they're very similar. Like what we're going to do is going to be repetitive throughout the three, other than cleaning data, obviously. So let's look at the business licenses data. So we imported that earlier on. I'm interested in restaurants and, bars and cafes and things. So this is why I took particular notice of business activity. There were a lot of these categories, so I did create my own business categories just to kind of lump some things together. And then, things that weren't important, I think I just put as unknown or something. Excuse me. This is an example of the data frame with just those two columns of the business activity. As I said, I created my own categories. I'm not going to walk through that and keep that hidden for now, but just know that I created a data frame, BizDF, that now has those new business categories. I called it BizCats New. And that this, as you remember, was a normal CSV file, so it was not a spatial shape file. It contained latitudes and longitudes for the business license, like where the business was licensed. And so here we want to turn this regular data frame into a GeoPandas data frame. Simply use GPD, geodata frame, put in our frame. And also we're going to use for geometry, we're gonna turn our longitude and latitude into a geometry. So we're using points from XY. And that's going to make it so that our lat long is converted into a geometry point in our geodata frame. And here we set the CRS. So this will create a GeoPandas frame that we can use similar to the other ones that I showed above. And according to my practice, this definitely isn't something you have to do, but I just found it helpful, especially with a lot of different data sets, saving business geom as its own column in case, I need to go back and forth between different data frames after I start, or geometries after I start joining the data frames. So now we have ShyBiz, which is our data frame of points for businesses. When you're plotting graphs, you know that you can layer two graphs just by plotting them. So we have our former Shy, which is the community level map. And then we plotted ShyBiz, which is those points. So we can see points of all the businesses on the map. And as you can see, it's saturated. But it tells us that this worked and that our business data frame is indeed a spatial GeoPandas frame where the points can be mapped to where they need to be. So that's good. Here I'm just changing geometry to block group instead of neighborhood. Excuse me. Here we are setting ourselves up to join our businesses onto the block group level data frame. So Shy is now block group level instead of community level. We're gonna do the same thing, make sure that the CRSs are the same, do the S join, intersects. We've seen this before, and this is pretty much what it will be as far as when it comes time to layering in those different data sets. Okay, so this is the data frame. Now we can see that our geometries are points. They are each business, with the business type, new business category. And then we also have it, which block group and which community group it's associated with, because we still have our community block and block group geometries, sorry. But we just have points, right? So that's not super ripe for analysis. It will probably be more helpful to know how many businesses are in a community, a block group in a community area. So just like a regular Pandas data frame, we're going to do some functions to basically group by and get counts of the businesses. So I create a business-wide data frame here. It's just a copy. And then I change block group to a string because you actually cannot do group by functions on a geometry type. So I change that to a string, and then I group by my geometry as well as my business categories because I want the counts by business category, since I'm really just interested in restaurants, bars, and cafes. So I want to know what type of business it is. And then once I do that, I make sure it's a normal data frame, and I go ahead and pivot it by business category so that each category is a column, and I will have the counts of how many businesses in that column for that community group. And this is the resulting data frame biz-wide. So here I have all of my business categories and then the count of how many of them are in this particular geometry, which a geometry is a block group because that's the level we were at. And then just to see here, a basic plot, we can color it by restaurant, bar, cafe, which is what I'm interested in. We're interested in, and you can kind of see the density of more restaurant, bars, cafes, downtown, near North. This is probably South Loop, O'Hare, things of that nature. So already we are starting to see how we can quickly bring some kind of visual aspect to our spatial data. Okay, so crime would be very similar. In our data set, we actually had different crimes like theft and homicide and other things. So it will be the same kind of functions we did with our different categories of businesses. So I'm not gonna open that. Here, we go down and we're going to start combining the data. That's what I'm talking about, layering all the data together so that it's kind of all in one place and just easier to analyze. So if you recall, we have our Chicago data frame, which has our community and block group geometries, let's say that. We have a CTA block group data frame. I didn't show you how I created that, but basically at each block group level, it tells the count of CTAL line stops. And then we also have our business data frame, which you saw us create. And yeah, you saw that above. And lastly, our crime data frame, which was created in a very similar way. As I said, different crime categories, homicide, narcotics. We have the counts for each of those in our block group level geometries. So now that we have our data sets, we can actually go ahead and merge them all as normal pandas data frames because all of them are actually at the block group level. So they all have that same column, which should have exactly, like if you treated it as a string, it would be the exact same string. So we go ahead and combine these data sets just as a normal merge with geometry as a string, because we converted above. Easy peasy. Above the map, I mentioned it was Cook County. Here, we're just making sure we're only looking at Chicago data and not Cook polygons. And this is the data set that we've created by joining those different sets together. We have CTA, L counts, the businesses are probably in here, and then our crime columns. Okay. Yeah, so I'm not going to spend too much time on the analysis part because yeah, it's pretty much the same sort of analysis that you would do with any data set now that we have a cohesive set. So some of the things that I did was correlation plots to see which, if any, variables were correlated. I have some insights here. I'm not going to go into those deep because we're running a little short on time. We have a scatter plot matrix, so you can more easily see any relationships between the different variables. I move into looking at some distributions. So for each of the different crimes, crime types, we can see kind of the distribution across census block groups, how they vary. in the percentiles. Also, arrest rates, I didn't even mention that, but that is some variable that I brought into the data. And then more distributions for the businesses, which are represented by some histograms. You know, obviously some block groups, you know, have a lot more businesses than others. Yeah. Okay. Looking at place. So here we're just gonna kind of look at the mapping aspect again. So we have our SHI-3 data frame that has all of those things that we combined in there. It's at the block group level. As you can see, with something this granular, it can be a little difficult to, I guess, pull some real insights. I mean, we do see some things here, like I said earlier, before I even got to the notebook, like theft happens more in the loop, and you know, violent crime happens more in the South and the West. So these are the representations of some of the insights that I mentioned before we dug into the notebooks. One thing to note is that, you know, zooming in and out, which I talked about before, can be helpful. So here we're building the same maps, but we switched our geometry to community level, and you can, you know, make some more sweeping statements when you have the data aggregated at this level. So that's why I mentioned wanting to have that ability to toggle between that more granular level versus, you know, a community neighborhood level. We're just able to see, you know, see a little better in comparison. And then another thing that I did was some bar graphs. Again, we can look at by community level some of the parameters and get an idea of, like, okay, theft. Where does most theft take place? We said the loop by looking at the maps, but here, you know, we can see clearly by the labels. One thing to note that I didn't do in this presentation is the maps I built were just normal, like Matplotlib. We could have used Plotly, which would have gave us the ability to hover on the maps and get the tooltips, so see the labels. That's one thing to think about if you were to embark on, you know, building your own maps, having that capability. So when you do hover, you could actually see information pop up. And if we have time, I'll show you that in something else. Okay, so the last thing that I want to talk about in the notebook is creating a area buffer. So recall that I talked about, you know, if I wanted to live near a CTA L station, because I don't want to have to drive, and I also don't want to have to walk too far, right? So I can create a buffer or radius around the point that is a L station. And to do this is relatively simple. First and foremost, know that this system does not work with miles. So you need to convert miles to meters. So I just made a quick little function here to do that. And then since we are now going to be dealing with distances, we need to change our CRS to a projected CRS, which I talked about before we dug into the notebook. So I converted all of my data sets to a projected CRS so that I could deal with meters. So we're gonna create this buffer of half a mile. I'm using my miles to meters function to convert half a mile to meters, and for our projected CTA, which the active geometry will be the point of the CTA station. So yeah, so for each point, we're going to draw basically a circle, a half-mile circle around it. That's essentially what we're doing. The code here to actually say which points, sorry, I want to know what crimes or businesses are in the half-mile radius of these CTA points. And this bit of code here will tell me that. I graded out, I commented it out because it took a while to run. But essentially know that you're doing a for loop across each of your CTA stations, X, and going through and seeing how many businesses or crimes happened in that buffer, in that radius. So I had just saved the data set, so I didn't have to run this again as CSVs. So then from there, this is just me making these CSVs back into GeoPandas again after I imported them, which you know how to do. And these are the data sets for businesses in buffer and crimes in buffer. So basically you will have your buffer, which is your half-mile circle around each station. And then you have every, in this case, business point that is in that buffer. And same for crime. You have your circle radius around a station, and then every point where a crime happened. And we've seen this format before, right? So it'll be helpful to kind of do the same grouping and pivoting that we did to get these points as counts, because we aren't super concerned with, you know, the individual points, but more of how many of them. And I believe that that is in here, yeah, where we convert those to counts so that we can get that. So I created a CTA buffer summary, which basically is my business counts and my crime counts merged onto my projected data, so that we can get this nice little data set here where we have our buffer, our CTA geometry, sorry, not the buffer, the L station, as well as the counts in our half-mile buffer for businesses and crimes. So now we have this data set. Like I said, it's very similar. One cool thing you can do is map it. So we have our CTA points. If you know Chicago, you know this. Yeah, this is the L system. It looks exactly like this. This is the blue line, red line. And then we can go ahead and do those count densities again. So this is the businesses. I only looked at restaurants, bars, and cafes. You can see that L stations around downtown have the highest counts of these things. And then up north has more color as well. And then same, I think I just changed it up. Same for this. I think it's a crime one. Okay, yeah, violent type crime. Again, plotting the counts on the CTA-L stations. In the loop, north side, more crimes on the near south side, CTA-L stations, west side. All of this tracks with some of the other maps we saw. But remember that these are specifically a half-mile crimes within a half-mile radius of these points, and each point is a CTA station. So that is it for the notebook. I'm gonna pause here for any questions, and then if we have time, I'll show you a prototype of the tool that I was building. It's not done, but just so you can kind of have an idea of where I was going with this. Any questions?
Hi, Lauren. We have a couple questions in the chat. So I'll read them out loud for you. One is from Jessica. She asked, Lauren, is there a way you would approach mapping a small space, such as a warehouse or a small factory, where the latitude and longitude could be almost indistinguishable from one room to another?
I'm sure it's possible, but I don't think this would be the tool. Because if you think about it, you would need a CRS that is going to account for the granularity of the space that you're trying to map. So I'm not sure that such a thing would exist for, let's say, a warehouse that may be very small. But that's a good question. But I don't think this would be the tool for that. I know that in my time at Walmart, so I worked in real estate, and oftentimes we dealt with in the store, like the real estate of the store, like when you needed to do repairs for certain parts of the store. Obviously, there are schematics of the layout of the store, and we would work with the real estate team to integrate that data into an analysis, but it wasn't geospatial. And I don't know that we generated any maps in Python based off of that. But yeah, definitely interesting and probably very useful question.
All right, thank you. We have one more from Lolo. It is, why could we not use EPSG 4326 for the projections? I don't know what that means, but I'm imagining you both do.
So I don't know the projections offhand. If you're saying why couldn't we, I'm assuming I didn't use that one. And that doesn't mean you can't use it. Like I said, there are specific CRSs for different regions. There are some more general ones. I know when I was doing this analysis, because I think I even had one grayed out or commented out like that I started to use and then changed it. So I don't know specifically which one you're referring to, what it is, but just because I didn't use it doesn't mean you can't use it. I hope that makes sense. Feel free to follow up if that's not a satisfactory answer to your question.
Hi, Kim. Kim is our favorite math teacher returning participant. Kim asks, are there any plans to make this into a dashboard? And I don't know if this is preemptive of what you want to show us, but
it is what I want to show you. So
great.
do we have any other questions? If not, I'll give you a peek of
That was the last one.
Okay. It's not done, Kim and everybody else, so don't judge me. So yeah, it's aesthetically, it needs some work. But I built this using Dash in Python, and also using Plotly, which I mentioned has that hover capability. So you see here now with the maps, I can actually see which community areas which. And this map is mapping the count of restaurants, bars, and cafes. And you can actually see the number here, 16, 71, etc. The way this is laid out is I have this drop down here where I can actually, or anybody can actually change which parameters they want to look at. I didn't do this in the presentation, but I mentioned that there were other variables that I looked at. Median household income is one of them. This drop down also changes the bar chart for by the community level. So again, you can easily see top and bottom. Some of the other variables I have, which these demographic ones I got not from Chicago Public Data, but from I think it's NGHIS. It's a government site where you can aggregate census level data. So that's another data set that I layered in, and you can actually select any of these to change the two plots above. And then I didn't even mention this, but another cool thing is that if you click on a particular community area, this bar chart for race and ethnicity proportions will change. So I'm a Black woman, and let's say I want to live where Black people live. This will tell me which community areas, what the demographic breakdowns are. Obviously, only 11%, 12% Hispanic here, majority white, 20% Black. You can look at other, Inglewood, South Side, mostly Black. So that's one feature of that. And then one of the things, since I imagined this tool as being where would I want to live, obviously we all have budgets. I played around with pulling data from realtor.com for active rental listings. And this down here, you can actually input or change your rental ceiling. So right now it's a very high number because I want everything to show. But let's say my budget is $1,300 for rent. I could put that in and it would update this map as well as the list of available rentals. It's slow, so give it a minute, but and then I could also update this map based off of theft, violent crime, restaurants, the things that I mentioned in the analysis that were important. I could update. Any questions with this?
You got a lot of questions. First of all, you got a lot of praise.
Oh, yeah.
Adding into that, this is great. And then you have some questions here. So Tasha asks, what's the name of the site where you aggregate census level data? I believe
It's in the notebook. It is in the notebook, in that section at the beginning where I had the data sources. That data source is actually in the notebook, even though I didn't walk through it. But I can look real quick and just put it in the chat, actually. Yeah, in NHGIS. I'll put it in the chat.
Thank you, Lauren. While you do that, Jessica asks, what do you use to host the server? Do you use Django, Streamlit?
So as you can see, this is local still. I haven't hosted it. I will probably use Streamlit because I saw some YouTube videos. It just seemed pretty simple. So I'm going for the path of least resistance. So once I get this to something live, I'll have to give you guys an update. Hopefully Streamlit is as easy as I think it'll be. Oh, and it updated. So you can see Inglewood is it also is filtered on Inglewood. Sorry. So it'll have to update again, but you can tell which block groups have properties under $1,300 if they're darker blue. The lighter blue are ones that don't have any rental listings under $1,300. Like I said, be kind, it's still a work in progress, but that's where we're headed. Any other questions?
Not a question, but this presentation is amazing.
Oh, thank you. Thank you, whoever said that. Cool. Thank you, everybody, for coming out and for all your questions and enthusiasm. And I hope everybody well in their data journey.